is different because when I put those two together, -5 times -1/5 is 1, right? And 1 to any power is 1. So the top is 1 and the bottom is root n plus 1. You good with that? Okay. Now you have the pleasure of demonstrating your expertise in finding convergence and divergence of power series. So you've got that sheet, you can do whatever you want, but to save you time, I'll go ahead and do what's going to work. I'm going to compare this to something. What does it look like to you? Doesn't that kind of look like 1 over root n? And what type of series is this? It's a p series, right? This is a p series. What type of p series? Convergent or divergent? This is a divergent p series because p is what? 1/2, right? Less than 1. So I'd like to compare it to this divergent p series. And the comparison that I'm going to run is the third one on the list, which is what we call the limit comparison one. So what I'll do is I'll just run a quick limit comparison. And the thing I do for limit comparison is I take this sequence and I divide it by the one I'm comparing to. Does that look familiar? Y'all understand what I'm doing on the sheet here? Flip. What am I hoping that this is going to turn out to be? What does that test say you really would like to have? A constant, a positive constant. So if this turns out to be a positive constant, then the result is that whatever this one does, that one does. So this is very similar to the one thing we just did a second ago. I can write them both underneath a single root, and then one application of L'Hopital on this, and we just get 1. Boom. Positive constant. So whatever this one does, that one does. So this what is it? Diverges. That means at this left endpoint right here, I don't want that as part of my answer, right? Because that left endpoint causes divergence. Do you all have questions? We done? No, we got to check the other one. We got to check positive 1/5. So let's check positive 1/5. Rewrite the series. Now this one I'll make sure I get it right here. When I put these together, I get -1 to the n on top, right? All right. What type of series is this? Or how do you want to handle it? What's that? Alternating series, right? Maybe the alternating series test? Yeah? So you have to check 2 things, right? You have to check that it's decreasing, and you have to check that the limit of that positive part of it goes to 0. And because, again, you're experts, I can trust that you can run the alternating series test on that. It will pass both of them, and that means it does what? Converges. Okay? Therefore, final answer, the interval of convergence. Oh, I didn't tell you I was going to use capital I for interval of convergence, did I? No, okay. I said find R and I. R was obvious, right? Because I said R is the radius of convergence. I'm going to use I for interval of convergence. So what is the interval of convergence? So -1/5 and 1/5, I know that, but here, parenthesis, bracket. That's your interval of convergence. Homework. Page 468. Hold on. This is 8.5. Page 468. Problems 3 through 21, all. Well, I'm pretty sure I did most of these on my homework video. I may have skipped a few in here, but if I did them, then you should be able to at least try them, right? So can you see how possibly on a test, like let's say a final exam, I could ask a question about this interval of convergence on a power series, and within that problem you would have to demonstrate not only your ability to use ratio test, but when you test your endpoints you might have to show me alternating series test and possibly a comparison test or maybe an integral test. It just depends on how I make the problem. So you talk about like killing like 2 birds with 1 stone. This is like I'd kill like 5 of them with 1 stone. Yes.
I just have a question. Like, why do the -5 to the n and the 1/5 n combine if they're multiplying?
Why do these combine?
Yeah, if they're multiplying.
Well, we have just a general property of exponents that if you have 2 things being multiplied that are raised to a common power, that's equal to, you can apply the power to each one of these. If that's multiplication, that's fair. So if we go backwards, we're going from here back to this. Make sense?
So x squared times x squared.
Well, if you say x squared times x squared, they're the same base. Here, these don't have to be the same base. But yeah, it would work with x, if you had x squared times x squared, then this should be the same as x times x squared, but that's x squared squared, which is x to the 4th, but that's x to the 4th. So yes, it still works. All right. We move on. The train just keeps going. 8.6. Writing. How are y'all feeling? That good, huh? Just how do you feel? I mean, we still have, what, 5 class meetings, including this one, so 4 left after this. We're in 8.6. We might see chapter 9. That'd be nice if we can see just a little bit of chapter 9 would be good. Writing functions as power series. All right, shifting gears here. All right? We're not going to be talking about trying to find the convergence or divergence or interval of convergence, all that stuff. Okay? We're going to now start and do something backwards. Before I had put up a power series and I said, hey, look, let's treat this like a function. What's the domain of that function? Now I'm going to give you more of like a standard function that you've seen before, and I'm going to ask you, can you convert it to its power series? So before we do this, recall this very important series. Now this was a power series. This is the first power series I gave you last class. This is really just summation n equals 0 to infinity of x to the n. And does anybody remember what this actually adds up to be? Does anyone remember what type of series this is? I mean, I know it's a power series, but it's a specific type. It's a geometric series. What do geometric series add up to be? When they converge, what do they converge to? A over 1 minus r, right? A over 1 minus r. Now, in this particular example, what's A? No, other way around. What's A? A is 1. So this should add up to be 1 over 1 minus, now, what's r in this one? It's x. Just look in your notes from last time. I did this, okay? Now, this is true if the absolute value of x is less than 1. So if you replace all of these x's with r's, you've got geometric series with a being 1. And then this would be 1 over 1 minus r, and the absolute value of r has to be less than 1. So we know this. We are going to use this fact extensively now, just to show you how we can use a known power series to convert functions that we know into their power series. So let's start with a nice little example here. Convert to a power series. All right, here we go. Here's the function, f of x equals 4 over 1 plus x. Now for this first one, I'm going to just kind of walk you through it, and I think you'll catch on to what I'm doing, and then the next one might be a little easier. So first I realize that the only thing I have to work with here is if I can get something to look like this, I can convert it to its power series. I don't quite have that, right? I don't have a minus down there. So instead I'm going to write it like this. First, the 4 I don't even need to have up in the numerator. I can just slide it off as its own number. And on the bottom, I'm going to force a negative by rewriting a plus as a minus minus. Right? Now, if you look at this formula over here, this x is kind of just like a dummy placeholder. And really, you could look at the formula as being 1 over 1 minus some box. And if you can figure out what this box is, this turns into 1 plus box squared plus box cubed plus whatever. So for us, this should convert over to 4 times sum n equals 0 to infinity of what, though? Remember what this was? That's the formula for this. So whatever's here, right? Whatever's there to the n. So negative x raised to the n. If the absolute value of what is less than 1, this is true. Negative x. So this is subtle, but it's very important. What I'm saying is that this function, right? This function that you would have studied maybe in college algebra, a rational function, this is equivalent, this is equal to this infinite series, this infinite polynomial, so long as the x that you're plugging in here, the absolute value of the negative x, is less than 1. As long as the thing you're plugging in there has an absolute value that's less than 1, then these two are identical. They give you the same exact result. Now, this actually is not written in its final form because this doesn't quite look like a power series. Remember, power series look like this? Right? That's what a power series looks like. So I'm going to do a little tweaking here. Is that the same? All I did was brought the 4 inside, okay? And then this negative x to the n, I rewrote that as negative 1 times x to the n, and then I rewrote that as negative 1 to the n times x to the n, right? Properties of exponents. So that's how this becomes this. Now, does that look like this now? Yeah? This piece right here, C sub n, is this piece right here, right? That's that number that's in front that keeps changing as n changes. Then do you have x minus a to the power n? Yes. What's a? In this case, 0, right? So I've created the power series. You see that? Convert a function to its power series. Convert that function to its power series. We're pretty much done. But just for, I guess, to show you, let's actually write out the first few terms of this guy right here. So start just plugging in n is 0, n is 1, n is 2, and let's see what we get. So if n is 0, negative 1 to the 0 is 1, x to the 0, 1, so 1 to, we just get 4, right? Now plug in 1. Plug in 1, negative 4, x to the first power, so minus 4x. Next one, plus, right? Plus 4x squared. Next one, minus 4x cubed, plus 4x to the 4th, minus 4x to the 5th. You got it? Plus, like this. I know that this looks strange, but yes, this is what I'm telling you, okay? I am telling you that this expression is equal to this expression as long as the absolute value of negative x is less than 1, which really means the absolute value of x is less than 1. So let's try a number. I'm just curious what happens here. Let's try something easy for us to work with. Something where its absolute value is less than 1. How about a half? Okay. What would happen if I plug 1/2 into this? Right here, f of 1/2. F of a half would be 4 over 1 plus a half, which is 4 over 3/2, right? Which is 4 times 2/3, which would be 8/3, I think. I worked really fast there, yes? 8/3. That's what that is. I claim that if you plug 1/2 into this, you'll get the same answer. Now, the only way to really check it is to get your calculator out, and we don't have enough time for this, but imagine plugging in a half here. Let's see what would happen. 4 half here, half of 4, 2, plus 1/2 squared, 1/4 times 1, or times 4 is 1, minus 1/2 cubed. 1/8 times 4 is a half, plus 1/2, that's 1/16 times 4, 1/4, plus, minus, where are we at? 1 over 32 times 4, 1/8, plus, you get the idea? If you get on your calculator and type this in, 4 take away 2, what's that? 2 plus 1, 3 take away a half, 2.5. Add this, 2.75, take this away. What are we getting closer to? What's that number? Isn't that, that's 2.666 repeated, isn't it? Right? That goes in there, 3, twice, 2/3, yes. That's 2.666. Weren't we like at 2.75-ish? As we keep going, this is going to start getting closer and closer to 2.66666. Yeah? But you're sitting there, I hope you're sitting there going, why in the world would you take a function that's so nice and turn it into this complete disaster, right, of infinite polynomial? Why would you ever do something like that, right? Yeah, computers.